Well, as you can see, the title of this little clip, The Common Ion Effect, it is not only an effect that happens with equilibrium, but we usually introduce it some point during our study of equilibrium. It also is common when we try to dissolve one salt or one solute in water, usually water, doesn't have to be water, but there's already something in the water. If that something in the water is in common with what is attempting to dissolve in the water, then what's trying to dissolve in the water won't dissolve in the water as well as it would have been, or as it would, if the water was pure water. So let's apply that, excuse me, to this situation. So I have some sodium fluoride, solid, dissolving in liquid water, of course, to make sodium ion and fluoride ion aqueous. And there'd be a little bit of an equilibrium there because not only does the sodium fluoride solid dissociate, but those ions might reassociate and come back together to make sodium fluoride solid crystals somewhere within that container. And that happens to a varying degree, but in any case, we need to think about the forward and backward equilibrium interplay of that. What we're saying here is, yeah, HF dissolves in water, but what if the water already had, so along those same lines, what if it wasn't NaF, what if it was HAF, I'm sorry, HF, hydrogen fluoride, hydrofluoric acid. Hydrofluoric acid you think might be strong, but actually it's technically not strong. It doesn't dissociate 100%, maybe only 5, 6, 7%, depending on the concentrations and such. The Ka is 0.00068. So if I compare the amount of this and this to this, you know how we always do. But the question now is, what if I don't just have pure water? What if my HF, 0.2 molar, is attempting to dissociate into water that already has some hydrogen ion? Or it could be already has some fluoride ion. Well, you see I set up my ice table in kind of a funky way then, where I say some of this wants to be created. Well, I want to dissolve some HF and dissociate some HF into water. But this will go up, and this will also go up by the same amount because this and this are created in stoichiometrically equivalent amounts from the dissociation of HF. So HF comes apart, makes one of these and one of these, and therefore the HF goes down. But because there's already 0.1 molar hydrogen ion, or I could make it 0.1 molar fluoride ion if I wanted to, in some sense this 0.1 molar hydrogen ion gets in the way, quote, gets in the way of the dissociation, or deters or limits the dissociation of the HF. And I set up my Ka like I always do, and the assumption is x is small. X is pretty small compared to 0.2. X is probably going to be small compared to 0.1 as well. I can check that. You see, I did check that. Assume it's small to make your work a lot easier, and I put 0.1 plus x on the top and 0.2 minus x on the bottom. Now there's another x on the top there. Assuming x is small here and here, I just ignore it and say 0.1 over 0.2. Do the math, and you find the fluoride ion concentration to be 0.00136. And I can take that x value and put it back up into my expression for the creation of a little bit more H plus ion. to 2 sig figs, which I had only up here anyway, 2 sig figs. The 0.1 is still very, very close to 0.1, and the pH is very close to 1. Yeah, right. The hydrogen ion concentration of 0.1 molar would be 10 to the negative 0.1 is 1, very close to 1. Interesting. And that pH of 1 is basically coming from this right here. It's not coming from the dissociation of HF. This is a trippy idea. If I only had hydrofluoric acid 0.2 molar, that would dissociate according to a calculation we've done similarly previously. It would dissociate to 0.011 molar F minus and H plus. The negative log of 0.011 is very close to 2. So we'd have a much higher pH, much different pH, but as compared to what we just had up here of pH of 1. But this pH of 1 is the hydrogen ion concentration that generates this pH of 1 is really coming from this hydrogen ion in water already. So in any case, I guess to summarize for at this point right now, again, trying to dissolve something in water that's already, the water that already has something in there. We can also do it as a demonstration. We take saturated salt water, NaCl, salt water, and we add a whole bunch of extra chloride ion from hydrochloric acid. This is Le Chatelier's principle. Do you remember that? If I have an equilibrium of solid salt and aqueous Na and Na plus and Cl minus, but if I add a whole bunch of extra chloride from, say, like I mentioned, concentrated hydrochloric acid, the chloride ion kind of pushes the equilibrium to the left, and I see that undissolving the association of sodium and chloride. I'll form some more, looks like a precipitate of sodium chloride. I bet I'll have time to show that to you in class sometime. That's why we go to class, see those silly demonstrations. As an example, let's take 0.1 molar of both weak acid formic acid and sodium formate. To what extent does formic acid dissociate? And we could also ask what the pH is. In pure water, formic acid dissociates like this. Kind of simple-ish calculation that we've seen too many times already. Assuming this x is small, x comes out to 0.0042. That's not, oh yeah, that is right, 0.0042 compared to the original concentration of 0.1 shows a 4% dissociation. That's getting close to where I really shouldn't assume x is small, but I'm going to go ahead and leave it that way because I'm lazy by nature, and the rule of thumb is if you're only 5% or less dissociated, less than 5% dissociated, is okay to assume x is small. I could do this with the quadratic and it'd come out to very close to 0.0042 anyways, is what I'm saying. So that's the dissociation. I could take the negative log of 0.0042, get the pH, find the pH of this acid, but what if I had that sodium formate already in the solution? So if this formic acid tries to dissociate into hydrogen ion and formate ion, but there's already some formate ion in the water, this formate ion will, quote, get in the way of this dissociation, and it'll be a lot less than 4.2%. Oh yeah, here it comes out to, we assume x is small here, x is small here. Let's see, this goes in the numerator. This I would have written 0.1 plus x and 0.1 minus x in the bottom. But assuming x is small, the 0.1's actually cancel if I have equal molar amounts of formic acid and formate ion. And yeah, okay, indeed, we see the dissociation went down from 4.2% down to less than 0.2%. Interesting. You could pause this one here and try it yourself. Here's acetic acid and the acetate ion. What if I was 0.1 molar in acetic acid and 0.07 molar in acetate? So I have 0.07 molar of this and 0.1 molar of this. What would be the pH? Well, if I didn't have the 0.07 molar acetate ion, then I could do that. This just like I've been doing in the weak acid units on weak acids, and the Ka is given to us, and we assume x is small, and basically it's x squared over 0.1 molar equals 0.00000018. That's the constant. Solve for x and take the negative log of x, and that's the pH. But if that's not the case, then we need to make an adjustment, yeah? The adjustment is put a 0.07 molar here instead of a 0. So this goes up a little bit, just as this goes up a little bit from 0 to something. This goes up and this goes up by the same amount, and this goes down by that same amount. Assuming x is small, we assume 0.07 plus x and 0.1 minus x are very close to 0.07 and 0.1. What's 0.000257 divided by 0.1? Man, that's still a small percent dissociation. So anyways, it works. And the answer is not much of this acid dissociates into water because that 0.07 molar acetate is already, quote, I say it a million times, getting in the way. So the pH would have been 2.87 down to 3, whereas now the pH is only 4.6. So the hydrogen ion generated is not nearly as great if some other ion is already in the water getting in the way. Oh, it's done! Yay! Go relax. Thanks for watching. See you in class or discussion.